Hello, welcome to ZenView Studios Lab. Eric here. This is the last episode on capacitor. We've seen a lot of details and things, how to measure capacitors and the influence of different aspects. We haven't touched on dielectric, which we will in this last episode. And before that, I want to go over about some theory, because to understand really you have to have an idea how all those measures relate one to each other. So I will try to make a little section on the theoretical aspect between the relationship between theta, tangent delta, which is the dissipation factor, the ESR, and capacitance and the reactance of the capacitance depending on the frequency. So to give you the perfect complete outlook that you ought to have to understand fully a capacitor and why we've seen the different things in the video. This will give you I will try to simplify it, but this will give you the general knowledge and relations between all these parameters you hear about, and what's their relationship and how to go from one to the other when it's possible, and what's their relation one to another. Give you also an idea why leakage current is related to dissipation factor, etc., etc. Voila, let's go about the video, and I hope you enjoyed the series. If you did, please don't forget to like and subscribe. Hope to see you soon. Now on to the technical stuff. So here we have the principal formulas that you need to understand capacitors. First of all, this is a representation of what a real capacitor is. You have some inductance, some resistance, the ESR, and the capacitor. To begin with, we represent with a polar diagram. I will go over it in a little bit. To make things a bit clear about this, if a capacitor was perfect, meaning without ESR and ESL, then on this diagram we would have an ESR which would be 0, and the arrow that you see here would go directly at 90 degrees and be a perfect capacitor. That would be ESR 0, perfect capacitor, not physical. A real capacitor has some ESR. The distance here, this vector is showing the resistance, and this other vector is showing the reactance. The reactance is the AC resistor that you have. We'll go over it again. In this case, this is a little schematic of what you see on one of those ESR meters. You have a theta, which is, for example, here 86.4. That's the angle that you see. It's minus 86.4, by the way. And to calculate the delta, which is the tangent delta, is in fact the dissipation factor. We'll go over it in a minute. The delta, it's the 90 degrees that you have between those two axes, and the 86.4, so it's 3.6 degree. So to get the dissipation factor, you take the tangent of 3.6 degrees. Plug that in your calculator and you'll get 0,0629. That's your dissipation factor. Okay, here is the relation that the formulas that relate between the tangent delta, which is also called dissipation factor. It's the same thing. It's just two different ways of calling it. Dissipation factor is what it is electrically. What it means is that the resistance will impair you from dissipating the full power. This is why it's called dissipation factor, you will not get the full power transfer because of that dissipation factor, because of that ESR. So the relationship here, it's written ESR is dissipation factor times omega C. Omega is the angular frequency in radian per second. The way to translate that, there's another formula, which I'll show you in another page, which says that omega equals 2 pi f. This is how you get to this side. You just replace omega by 2 pi f, and there you have dissipation factor over 2 pi f c, the capacitance, equal ESR. This is how you calculate ESR that you see everywhere. Now the most important part is that you understand that the reactance, meaning this amount, is frequency dependent. This is why we said that if you have a frequency that will decrease, you will have a reactance that will increase. And this is the formula that makes those two together. So the reactance, this length here, it's 1 over 2 pi fc. Same way, you can transform that and get C out of that, and then you can have C, the capacitance, is 1 over 2 pi f multiplied by the reactance, meaning if you know the reactance, you can calculate the capacitance. What you see here in the relationship, interesting, is for the measurement we showed with the ESR meter, when the frequency goes down, the capacitance goes up. This explains why you have different measurements with the same capacitor if you change the frequency of measurement. When we lower the frequency, we increase the capacitance measurement. Now the reactance, it's the same thing. This is frequency dependent. We say frequency goes down, reactance goes up. Okay? So this schematic here. Here it's the full explanation of this. You have the ESR, theta, it's the angle that, the ESR and the minus j omega c, which is this part, because in fact it's a capacitance. If it was an inductance, you'd go this way. If it's a resistor, you go this way. This is what a polar diagram is about, showing you on a polar diagram how is the different part of the impedance. Impedance is defined here. It's in a complex form where this is imaginary and this is real. You have the real part, the resistance, and the imaginary part. Depending whether this is positive or negative, when it's positive it's an inductance, and when it's negative it's a capacitance. But you can have the absolute value of that. This is how you calculate, and you can have the impedance. This is another way to get to the impedance. Remember that you have also the relation between tangent delta and the ZR and ZC, which is in fact the impedance, the reactive part and the resistive part of the impedance. That's the relationship between the two. Many ways. This is to show you there are several ways to present always the same data. What you have to keep in mind is when we talk about theta, it's directly related to delta, the tangent delta and the dissipation factor. So whether somebody presents you on an ESR meter minus 86.4 or tangent delta result, which is 0,0629, it's the same thing. It's just a calculation that brings you to a different part of the equation. This is the most important part, is that this is the relation between reactance and frequency, and capacitance and frequency in the measurement. That's very important. This is what we saw. And this is all true if the frequency that we use is well below resonant frequency. Because a capacitor, I won't go in, it's very complex, and it in fact has a resonant, they all have resonant frequency, and after that it rises again. I'll link to several papers if you want to read more about the mathematics and the electronics, I mean the physical explanation about capacitors. This gives you a better idea, I think, of how one measure relates to the other, and this is why we switch from one to the other, and this is why we have always to look at the frequency that we use to measure, and why we get different results whether we're measuring at 100 Hertz or 1 kilohertz. This is explained right here, okay? And this is the same thing, so the same with ESR and dissipation factor. And okay, one thing I didn't mention, the dissipation factor, I said it's related to the leakage. Yes, obviously. The more this thing it goes up this way, the more leakage you have, because this means the resistance is going to be higher, and this means impairment to the power dissipation. This is the contrary to this from the dissipation factor, and that's the quality that 1 over Q. This is something I don't discuss here, but that you might hear also about capacitors, is the Q factor, which is in fact 1 over 1 over D. I mean, it's the opposite of D is 1 over Q. Let's see. Let's put it this way. So this is relation between this, and the important thing to understand is that this is why you can measure dielectric, and I will show also in a graph that you don't have to just invent what the measure of impedance of resistance should be for the dielectric. There are rules for electrolytic capacitors, and it should be you will see in the 10 megohm, this is what you should obtain. If you get much lower values, obviously a capacitor is bad. This is what I was, and I will show you with the following part. Voila, we've got all the mathematics, and I'll show you the next page, which is right here. You can have that also. This is just a reminder of the things that we use. All right, so now we do the last test, and this is with this Megohmeter. One thing it can do is measure impedance, I mean resistance between 0.1 meg and 20 gig. And it has a voltage indication here, that you can change. So this is only meant for high voltage cap. It has an interest because, as I explained, a 200 volt cap might not fare the same way at 1 volt at 200 volt. For a quick test, we'll run it at 50 volts. So what it does, it will raise here the voltage of the cap, and you can see it happening here, to 50 volts. I can do it to 100 or 250. This, the limit here is 200. And now it's starting to measure as soon as it reaches 50 volts, how many megs it sees on the cap. If there is a problem, you will get a low impedance, not in megs. Here at 50 volts, this is reacting fine. Okay, this means that the capacitor, even though previously we said it's not so fantastic, well, it's dielectrically speaking, and it's still okay. There's no problem. It's still good. The age is probably explaining that we have a little bit more loss than we ought to, but that's it. Okay, this was, see, 10 meg at 50 volts. I can go to 100 volts, and we get the same thing, except that now we raise the voltage at 100 volts. And we'll get a measurement of the capacitor's dielectric and resistance. In fact, we're pushing 100 volts to see what happens and how it reacts. You see, it's anyway 0.200 kilo it started, and it's now in megs, and it's raising and going up. This is perfectly all right. This means the capacitor is good. and will go to maybe 10 meg or whatever if we leave it long enough. Okay, now in 30 seconds we have reached 5.66 meg or so, so I can stop the test. Okay, never forget when you do a test like this, okay, this is charged. First of all, this thing is not meant to do what I did. So you have to figure out if the leads that I'm showing, plus and minus, are really plus and minus on the unit. Let's see if you can see that. This is a little trick that... And in fact, it's reverse on this MH12 ANEG. The plus, it looks red and it should be red here. I mean, it should be plus here and minus, but it's exactly the contrary. How do you know that? Well, simple. You just put a voltage meter. If it's AC, it will not show it, but we can see first of all what happens when we do the testing. Okay, it's showing 6 volt AC. Okay, and now if we put a DC voltage measurement, 100 and plus 101 volt. This is what it says also here. So, I'm sorry you didn't see that. I will show you on the with the zoom out. Maybe if we can manage. All right. Now you can see in the back all the way, I hope. Let's see if we can move this a little bit out of the way. 101 volts. That's what the unit outputs. And it says 10 megohm because that's the input impedance of the multimeter. That's correct. Okay? And so this is what I just told you, is that if you ever want to duplicate what I did, be sure to check where is the plus and the minus before you put it on an electrolytic capacitor, or you'll blow your capacitor. All right, so that's the first thing. So we showed here that in fact these capacitors that were supposedly bad, they have a difference in the D tangent delta of the dissipation factor of the capacitor is worse on these capacitors which have a older age than the normal ones. There is a difference. This is why they were changed, but it's not that great. This is what you have to understand from all this video, and that's what I try to do to explain in the video, is that in fact the changes are subtle, and you have to have a good understanding of ESR, frequency, dissipation factor, and how they relate to frequency, one another, and which frequency you ought to use to test which capacitor, which voltages, and so on and so forth. None of these measurements alone, one value like this taken out of context, is significant. This is what you have to remember from this, and you can build your own judgment using rather than tables, using tests, just like I did. This is one very simple way to have your own feeling of what this ought to be, comparing to new caps. This is one thing you will always have. If you do new caps, then you will know exactly what if you compare it to new caps, you will know what the value should be. You can test in circuit also. This will give you an idea if you need to replace a capacitor or not. That's very important. Voila, that's a little bit roundabout. We saw that a bad cap, you can really tell. The capacitance is really off. I didn't go very much about film caps. We can just before we leave, check this. Here, it's 16 ohm. Am I doing something wrong? Yes, I'm doing something wrong. This is what you should check. This is a 220 nanofarad, 225 nanofarad capacitor. What did I say? Smaller cap, higher frequency. Okay, so a good measurement will start at 1K, certainly not at 100 Hertz. Okay, and how? Now you see 2 ohms ESR, and dissipation factor is way down to 0.031. And probably, since this is a very small cap, the 10K which we showed was equivalent to 100K is the real measurement that you ought to do. Okay, and here we have only 170 milliohms, dissipation factor of 0.024 and 224 nanofarad. Okay, so this is, don't forget when you make measurements, proper frequency for proper cap, depending on the size. Okay, and lastly, if this was a bad one, so let's see if we change it for the right reason or not. Yes. What's wrong with this one? 1.5 ohm ESR. Dissipation factor is good, but the ESR is bad. This cap has gone. This is exactly because we just measured something similar in not far away. It should not be such a big difference. An order of magnitude like this, it's too much. So this means this is gone. Okay? This is how you judge. Voilà. Here was a quick lesson on how to test and see for yourself and build your own judgment on good or bad capacitors. Things are not quite as simple as people want you to believe. You have to build a judgment. I hope you enjoyed the video and see you soon. At last you can see a graph with the expected resistance from capacitors, namely electrolytic. This is what we measured, and this is confirmed by what we read here. 10 megohm is what's expected. You can see also that other capacitors have much higher resistance, insulation resistance. This is part of an article whose links you can find in the description of the video. Thank you for watching.